At the end of the last video, we discussed image stacking and a little bit on image integration as part of the batch pre-processing script. We perhaps should just take a few more minutes to look at integration and how to improve upon those results. So in processing, image integration tab, there's the image integration tool. If we load it up with the images, the registered images, you can see here it says corrected, cosmetic corrected, debayered, weighted, registered. These files are ready to be integrated basically. If I collapse that and bring up the format hints, it doesn't need to know this because it's already built into it. On the image integration, you're going to choose typically average. There are other options, median, minimum, maximum, but average is normally the best. And then normalization underneath it. So when the images are averaged together, they are matched more closely in terms of tonal distribution. And the way to do that is additive with scaling. So there's a gain factor and an offset factor to basically make the images similar. And bear in mind that if you scale something or you add a pedestal, you don't actually alter the noise because you're altering the signal at the same time. It doesn't necessarily add all of the frames with equal weighting. There is now a weighting and there's something called a noise evaluation, which it can do for itself. Or you could, for instance, if you've been using one of the other tools to give you a weight based on a number of different parameters, you can put in the weight keyword that's in there, and again it will use that number instead of generating a noise evaluation, which, to be honest, up to this point is the one I've always chosen, typically because I'm doing deep sky imaging of nebula and noise is the overriding factor of goodness. And in terms of working out the scale, it looks at how to work it out using statistics. I leave it on the default one here, which is this iterative k sigma one. And again, if you want to do the default settings, you hit this little funny X button in the bottom right hand corner. The other options down here, you want to generate an integrated image, you want to subtract pedestals if they're defined in the image itself, it's going to evaluate the noise, and there's some things about buffers and file caches. This is quite handy because the last set of results and images are held in memory, so that if you want to re-evaluate image integration with different parameters, it doesn't have to go through all the computations from the disk each time. It can take an interim result from memory and process them much more quickly. So if I collapse that and then look at rejection, this is how it decides which pixels to reject. Again, I would use the default, which is Winsorized signal clipping, which works for 15 samples or more. And normalization, again, to decide what is an outlier, it needs to make the images broadly equivalent. So it's doing a scale and zero offset, and it's going to generate some rejection maps so you can see what it's got rid of, and it's going to clip low and high pixels based on numbers of standard deviations and the low range. Collapsing that, this one here brings up the actual rejection parameters. So you've got the statistical rejection of values that are lower than expected and higher than expected. And I typically have values here anywhere in between 2.5 and 4 sigma. This parameter here was introduced in a recent version. I leave it at the default at 5. And on the low range, I have a very small value here just to make sure I don't count black pixels into the averaging process. So if I collapse that up, the ones here are based on CCD parameters, which we're not worried about, and I don't need large-scale pixel rejection either. So what I now can do is say apply global. I ran this earlier, it's done a lot of the computations already, and now it's just using the stuff in its memory buffer to calculate the final numbers. And it will take a short while to do them all. And the reason it's doing it 3 times is because this is a color image with red, green and blue pixels. And then it does its noise evaluation, and then it actually does the integration. So I'll come back in a few moments when that's complete. Right, so that's done, and I'm just going to put that over there for a moment. So we have a number of different images put on the display. We've got the high rejections, which don't appear too many, just a couple of little random dots. We've got the low rejections, which have got some random dots around the cluster, probably because a couple of the results had much smaller star sizes than others, so therefore appears to be a statistical anomaly. And finally, the one labelled integration is our actual end result. And if we stretch that, we're going to get the cluster back. The other thing to note is that in the process console, it tells you what the noise reduction was. So 1.066, 0733 and 728. So if I run the integration module again, bring up these parameters here and change that to say 4 sigma in, or 5 sigma in this case, and rerun it, I'll get a different set of results. And that may be an improvement on the previous set of results in terms of noise reduction. So if I look at the process console, the median noise reduction was 10751 in this case, and in the previous case, if I scroll up, it was 10522. So as you'd expect, because I've included more pixels and rejected less pixels, the noise reduction is slightly improved, but not a great thing. That's the bit about integration, and what that gives you is a stack. So let's just get rid of that for a second and bring up a stack. So this is a stack of 130 frames. The previous one was just a few frames to keep things nice and quick. If I take off the screen stretch, this is the linear image as it appears naturally. So you've got 3 white dots which correspond to the brightest stars and a very, very faint patch in the middle, which is where the cluster is. Now, this is a color image, but when you come to do linear processing, you may have several images. So on this workspace here, I have a set of images which are all linear stacks. They've all been screen stretched, as you can see from the green bar. And here I've got hydrogen alpha, green, blue, sulfur, oxygen and red. You would be doing linear processing on all of these files before you got to the nonlinear stuff. So what's all this stuff about linear and nonlinear? Well, I'm going to take a slight detour to explain. For the last couple of decades, we've all been used to using film and paper, and it automatically recreates the scene that we can see, with a bit of tonal compression in the shadows and the highlights. When we started to use digital cameras, things became a bit more complicated. At the beginning, most cameras only produced 8-bit image files, which only give 256 levels. And while that sounds a lot, if you didn't alter the data coming out of the camera, you would see distinct banding of the tones at one end and not at the other. And what has happened with things like Photoshop and any consumer imaging device is that the tones from black to white are remapped across the 256 levels so that they appear as equal intensity changes to the human vision. So let me show you what that means to an ordinary consumer camera file. So this is an EOS RAW file brought in to PixInsight without any modification. On the back of the camera, it showed a number of bright white dots corresponding to a very famous star cluster. But take away and strip away the manipulations that are done automatically by the camera, and it appears black with a couple of dark grey dots. And it's only when you stretch the image do you actually see what it's there, which is M45. And this is what we've traditionally used in Photoshop and other programs like it, and it's called a gamma adjustment. And the best way to demonstrate that is using something like the histogram tool. So if I bring up Process Histogram, now this is very, very similar to the Levels tool that we use in Photoshop, and it has a white point, a black point and a midpoint. So I'm going to click on this one here that looks at all tones equally. You can see that this is a mid-grey, and most of the tones are distributed in this very, very dark mid-grey, which is down here. So I'm just going to take away the screen stretch and play with it. So I'm going to put the preview on, and I'm just going to drag this slider in the middle. And this is what typically would happen on the back of the camera, and in Photoshop it will apply a gamma change, and it will boost the midtones but leave the white and the black tones unaffected. And this image now, if I applied this, would become nonlinear. I can still alter this image tonally and keep it linear by resetting the midpoint, but just altering the white point. A different result. The darkest tones are very similar. The midpoint is dragged down, but you can see that the straight line transformation means that all the tones, if a tone was double the last tone, it still is double, it's just over a shorter range. So linear imaging doesn't mean that you can't alter an image tonally, it just means you can't do it in a non-linear fashion by altering the mid slider. Now, why is that, and why is this important? Well, let me just cancel that for a second. Some tools really prefer working on linear images before you've distorted the tones. One is the color correction tools, because once you start amplifying and distorting color issues, they're far more difficult to get out of the image. A second is deconvolution, which is a process that can try and bring back better resolution than in the original image. Another one is taking some types of noise reduction, work best on linear images, and also trying to get the color balance between different monochrome files is also a good way of doing it, is in linear imaging. And the same with this one. With a color image, it's also true that if you want to try and get a neutral color image, then it's sometimes useful to do this in a linear space before you start stretching it and making it more apparent. So let's have a look at some linear processes. Let's take a look at my stack of M3. This is a color file. You can just about make out that the margins are a little bit on the green side and there's a bit of a magenta wash over here. Now, typically what you would do before you start doing anything to an image is I would crop them. This is easy when you have a single image like this, and you would do process, geometry, dynamic crop, and you choose your area that you want and you'd hit crop and off it would go. And the reason for that is twofold. One is there's no point spending ages trying to correct things in the margins that can be trimmed off anyway, and secondly is that some processes use the image itself to calculate values, say for instance calculate the background colour, so you don't deliberately want to include parts of the background that are an oddball colour because it'll distort the final result. So I'm just going to cancel that for a second and take a slightly more advanced look at dynamic crop when you have multiple images. So if I look at multiple images, as in this case, if I want to do dynamic crop on these, we have a very difficult problem here because I want to crop each of those images which already registered to each other so precisely so that when I eventually combine them to form a colour image that I don't have any misregistration. And so one of the tricks about dynamic crop is that you can apply exactly the same to each one. So let's bring it up again, geometry, dynamic crop. And what we would do is we'd select the crop on one image, so just the tip of the elephant trunk neck here. But rather than hit this little tick button to say apply, I'm going to drag this down to here as an instance. I can close this now and get rid of it because all the information is now stored in this process icon, and now I can drag that process icon to each of these images in turn and apply exactly the same crop to each of these images so that now when I put one on top of the other they're still exactly registered to each other. So that's something just to watch out for when you have multiple images that are meant to be all aligned to one another. You need to crop them identically. Let's go back to the image of M3 and look at how we would process it. So this has been screen stretched with equal stretching on red, green and blue channels, which is making the light pollution look that much worse. One of the first things we want to do is take away this red background, and you can do that a number of ways, and principally the one I start with is background neutralization. And this tool will take out the red in a linear process by altering the black point for each of the channels. Before we do that, however, it's wise to take a look at the image with a customized stretch so that we can see what the image looks like. And if we look at this, you can see that even though I have use flat files in my image calibration, there is still a sort of weird margin around the side, and really this isn't adding much to the image, and it's getting noisy towards the edges where the overlap between successive images wasn't perfect. So you would normally crop this out. If we just bring up dynamic crop once more, I'm going to make a crop which is 3500 by 3500 pixels. And I'm going to shift the center to the middle of the cluster. That makes a nice image framing wise. These big stars are contained within it, so there's no big stars on the margins, so that's good. So let's hit tick. So now we're dealing with a much smaller image which has no rubbish around the outside that's going to affect some of the processes, because some of the linear processes, and even some of the nonlinear ones, they use the data itself to decide how to react, and so you don't really want it reacting to poor data. So I'm going to close this down for a second, and under the background neutralization tool we're going to very simply tell it how dark is the background. So if I put my cursor on the background here and read out along the bottom, the red is 0.008, which is higher than the others, which are 0.005. So I'm going to make it 0.01, which is up here. That's going to be the upper limit of the background. And I'm just going to use the whole background as a reference. Otherwise, what I'd have done is create a small preview and then reference that preview in the background reference image. Just so that you can see what's happening, if I shift click this, I go back to the standard stretch, and then when I apply this, it goes sort of neutral, but we don't really know until we've hit this button. So that's a standard stretch applying equal stretches to red, green and blue channels. You notice that the whites haven't changed much, but the background is a lot more neutral now, and I've in effect changed more than anything the black point setting on the red channel so that it clips off the light pollution. So that's the first nonlinear process. Another one might be color calibration. With the color calibration tool, it uses two references, one for whites and one for background. So again, if I look at the background, all my levels now are a little bit lower because of the background neutralization, and they're typically lower than 0.004. So I'm going to put in 0.004 in there, and for the whites I'm going to choose something a bit higher than 0.004, so I'm going to put in 0.009 as a reference lower limit for white. So what it should do now is it should subtly alter the colour balance between these two to keep the background neutral but make the whites slightly more neutral overall. So when I drag it onto there, it's showing me the stars that it's actually doing because I've ticked this box here, so I can get rid of that for a second, untick that box, and you'll notice that now I've got a range of stars. I've got some more bluey whites, I've got some creamy whites, and so therefore it's really changed the colour balance between the whites and the darks. In fact, the darks are even more neutral than they were before, and that's quite a good result. So again, if I shift click on here, you'll see that that's a fairly neutral star cluster now, and the small amount of colour in there, I can increase the saturation later on. The other thing that you might want to do, which is another linear process, is to improve the background. There's some slight colour shifts. There's a bit green in this corner here and it's a bit red in this corner here. To fix these small colour issues, I would use another linear tool which helps with colour balance and gradients and calibration. And it's called DBE, or Dynamic Background Extraction. So under Process, it appears under Background Modelization, and then is Dynamic Background Extraction. It has a number of ways of using this. There's a semi-automatic way of using it which generates sample points across the image and tries to work out what's background and not. I prefer to do it manually by clicking on the image and then clicking carefully in areas of background where there are no stars. If you click down here and expand this, you can see the sample it's just taken. If I click on the star, you can see it goes black, which is obviously bad, so I can delete that sample back out again. When you click on the samples, if these little crosses on the screen go red, it means that it thinks that the sample value is too far out of tolerance with the other ones and rejects it. And that's because, if I just collapse that and expand this, there's a tolerance value. And you can basically open the tolerance up so that it accepts more wildly spaced samples in terms of colour values. These ones are all good. There's a couple of little green samples along the bottom here I'd like to include. And once you've done that, I would, without any of these things at the moment being ticked, I would just hit the tick bar. And what it does is it produces a background image. And if you click on this background image and then stretch it, these are the colour values that it's going to remove from the background, so it's going to subtract them away. So a little bit of green at the top, and the reason that they're so distinct is because we're talking about very minute changes. So I'm going to close that down for a second, and then I'm going to do subtraction and discard background model because I've already seen it, and I'm going to replace the target image and then hit click. And what I have now is an image whose background is better still with less colour gradients on it, but the whites have not changed. So that's another process which I would do on a linear image, and it would not affect other linear processes like deconvolution, which is going to be the subject of a separate video because of all the tools it's probably the one most complicated. But just to finish up here, there are a couple of other little things you can do. One of these is called Multiscale Linear Transform, or MLT, and there are two very similar tools. One works best on linear images and the other one is probably, fair to say, optimized for nonlinear images. What this does is it allows you to emphasize or de-emphasize different parts of the image based on their size, their scale. So a small star is small scale, whereas a big nebula is big scale. By emphasizing small structures, you can make it appear sharper. By reducing the noise level of different scales, you can, for instance, take out pixel to pixel variation, or if you've got blotches, you can take out something with a much coarser noise pattern by changing the noise level of a coarser scale. These numbers here are done in layers, so basically what it does is it splits the image internally into different structures, in other words big blobby ones and then smaller blobby ones and very small blob ones and then tiny point sources, and then applies different levels of emphasis and de-emphasis and noise reduction to each layer and then pulls them all back together again. I would typically do this on a few images where the background noise is objectionable. This one's quite good already, and I would do little and often with noise reduction, the same as with sharpening. You don't do it all in one go, you try and do little and often as you go through. But for linear images, my favourite noise reduction algorithm is not applicable, unfortunately, to colour images coming off a colour camera, but it does work beautifully with monochrome images, and it's called the Muir script. So under script and noise reduction, it's called Muir denoise. It has a very, very simple interface, but it is applicable to monochrome images. You choose the view, so I'm going to choose one of my monochrome ones, my Hydrogen Alpha stack. You type in the number of frames that it's made up of, so if it was 50 frames, and the way it was registered, what was the interpolation method, which is reported out in the tool and on the console. Normally it's Lanczos 3, and here you plug in the parameters for your camera. So these parameters here are for the Kodak KAF 8300 chip with a gain of half and a Gaussian noise of 16 ADUs, and that's the parameters for the camera. If you don't know those parameters, there are other tools that can give you those data by comparing to dark frames and so forth. And you just hit the word denoise and off it goes. It takes about a couple of minutes and the result is remarkable. So it's using camera characteristics or sensor characteristics to work out what is noise from the sensor, and it removes it. And that again is a linear system. It's not doing any multiplicative work on the image, and so therefore it's safe to do that before the king of them all, which is deconvolution, and the subject of the next video. Thank you for watching.